All right, so those of you who are here, hopefully you're on, oops, wrong view. Hopefully you're in kind of the Friday class. And then Monday, those of you who can show up Monday will be right here on the Monday list. Now, I don't know if I'll get it completely done this weekend. I'm hoping to. I'm going to put a survey, like a quiz up on today's online quiz. Will be a couple questions like just about you, like what's, are you a freshman, junior, sophomore? What's your major? Then one of the last question will be whether or not you want to attend in-person classes, right? So that way, if there's anyone who knows that they're not going to be able to, I've already got a couple emails, then I can kind of limit the list and maybe we can get in here more than just once a week, right? I also tentatively will throw this out there, and I'll post an announcement on Canvas if it happens. I think there's a lot of empty rooms downstairs that have a slightly higher capacity. So I might move us to one of the rooms on the main floor in this building if I can get verification that they're open for the rest of the semester. So be looking out for an announcement on Canvas about a room change if I can make that happen, hopefully. All right. So left off last class, I think we just kind of got this far, right? So we were talking about different examples, talked a lot about the kind of summarize the syllabus. One thing I said you need to do, get on, get that access code by the end of the week and get that first Learn Smart done before class starts on Monday. So 12 o'clock on Monday would be the due date, okay? So let's kind of dive into some actual material today. And for today, I won't be kind of having the whiteboard behind me. I think for in the future, I'm going to set the class up. I'm going to take one of those empty tables and pull it up here so that I'll kind of have the whiteboard behind me. I shouldn't have to do a whole lot kind of on the board today. If I do, I'll use that kind of Zoom feature where I can kind of write a little bit on the screen. So I have this kind of data set of kind of a truncated roster for the Chicago Cubs, right? So this was ever since they won a World Series, I feel like I can admit to being a fan of them. So, it doesn't really matter that this is kind of a sports-related data set because if we look at kind of what we have here, we've got, I think it's 10 different players. We have their name, what position they played, and their salary, right? This could very easily be 10 other random names at Deloitte, their position at the company, and what their salary is, right? So it doesn't matter. This is a Chicago Cubs roster. This could be the roster for any company, right? So we'll think about every single one of these lines, these rows, is an observation, right? So here's my very first observation. I'm recording information on 3 variables, right? So we'll call the rows an observation, or you might see in the book, or if you do like Google, sometimes they'll call this an element. The interchangeable words, I'll always say observation. And then we collect information on those observations for 3 different variables. So our columns are variables, right? So our variables here are player name, position, and salary. Okay? So our columns will be our variables. Our rows are going to be our observations. So we can collect information on very different types of variables, right? So there we go. The very kind of first 2 categories we'll talk about is we've got qualitative and we've got quantitative, right? So qualitative, basically think of these are kind of words, right? These are descriptive, characteristics about an observation, but they're really just going to be non-numerical. That's the easiest way to think about it. And then we have quantitative. That's going to be a variable that we record that is numerical. So an example of a qualitative variable would be if I had like a used car, and let's say I'm managing a used car lot, and I've got all these cars. I've got the color of each car, red, blue, green. The color would be a qualitative variable, right, that I'm collecting. If I then went around and collected the mileage that was on each used car, that would be collecting a quantitative variable because that's a number, right? It's numerical. So I don't know, there's an easy kind of way to kind of remember the distinction between the two. I always think of, quantum physics involves a lot of math, so quantitative must mean numbers, right? I don't know if it's a goofy kind of way to remember it, but sometimes that's a way you can remember. So qualitative is a variable that we're collecting words. Quantitative, we're collecting numerical values or numbers, okay? Any questions of those? Those shouldn't be too bad. So we've got kind of the 2 main categories of variables that we'll be collecting, right? The very first kind of breakdown we can look at is take those qualitative variables, right? So qualitative, those were the words, right? The variable that we were collecting words on. There's two different types of qualitative variables. So the first is going to be nominal. All right, nominal variables basically are some variable that we're collecting that really has the response to it has no intrinsic value, right? Knowing the color of the car doesn't allow me to rank them, doesn't allow me to order, really order them other than like order all the same color cars together. And so there's really no, we could say, intrinsic value to this variable. Right? We can't really rank or do anything to the observations. So some examples of this, if I was collecting a data set in everyone in this room, and I collected something like hair color, right? So the responses could be black, brown, blonde, red, blue, whatever. But it doesn't really allow me to like rank people based off hair color, or at least that would be kind of a frivolous pursuit. And so this is a good example of a nominal variable. A lot of times we collect the gender. If we have like a survey, once again, nominal kind of qualitative variable. The data set we're looking at earlier, baseball positions, right? It was just a word. It would have been kind of an example of a nominal variable, or even player name there, right? Was a nominal variable. Okay? So, these don't have a lot of power, right? It tells us something about the observations, but it doesn't really allow us to calculate many statistics, right? So here's we'll go back to the old data set. We had these two nominal variables, right? Position and player name. Ordinal variables are a little bit more useful, right? So ordinal variables, right, they're still qualitative, right? So they're still non-numerical, they're still words, but it allows us to kind of rank the players. And there's some intrinsic value associated with that ordinal variable's value, right? Or if I say value, or whatever the string of words is. So some examples of this would be, when you do kind of teacher evaluations, and they ask you all these questions, one of them is, this is an effective teacher. You've got 5 options, right? Strongly disagree, neutral, agree, or strongly agree. Now, those are still words, right? So it's still qualitative, the responses I'm going to see for this variable. But I know that someone who strongly agrees with this statement thought that it was a better teacher than someone who disagrees, right? I could actually rank kind of the observations based off this response, right? Because strongly agree is more than agree, which is more than neutral, but they're still not numbers, so it's still a qualitative variable. Other examples might be if you ask them what their highest level of education is, right? Well, it's a word, right? Because we typically don't ask people the years of education. We ask them like, what's their highest degree? So I would still have I'd have a qualitative variable, but now it's ordinal because based off the responses I see for this variable, I can rank the people in terms of most to least education. Any questions on that one before we keep moving? Okay, another really good example of an ordinal variable are letter grades. If I'm not able to actually observe the grade, but just the letter, well, I can rank the grades, right? I know that A's, are higher than B's, but within every student who got an A, I can't tell you if one A is higher than another if all I can see is a letter grade, right? Someone could have gotten a 94, someone could have gotten a 99. I don't know, right? So it does give us some power, right? But within each response that we could see for the variable, I can't rank them within each response, right? Just kind of comparing the different responses. Can I compare them, okay? All right, so we've got kind of 2 types of qualitative, and one way to think about this, actually, let me throw a blank slide in here for us to use. So one way to think about this, you think about, let's see if I can spell. We have qualitative variables, and then kind of in either direction, we have 2 different types. One, which is nominal, and then, there we go. Another type, which is ordinal, right? So this is kind of how we're thinking about this, right? These are both qualitative variables, right? They're just a little bit different because the one ordinal allows us to kind of rank them, okay? All right, we'll clear that. Actually, I'll give you a second or two. Shouldn't be too bad. So we're next going to break down quantitative variables, right? So quantitative was when we have the numbers, right? Numerical values. So the first one we're going to talk about is discrete, right? So I'll put some examples up here, but I think the easiest way is to think about a number line, right? So for a discrete variable, we could see a 1, we could see a 5, we can't see like 7.8, right? So for a discrete variable, we're only seeing the integer values, or the values that we could see, there's some gap in between, right? So typically, almost every example we're really going to be looking at, the gaps are that we can only see the integers, right? So questions like the number of siblings you have, right? 0, 1, 2, 3, 4. How many days you consume alcohol each week, right? 0 through 7, right? You can't see 2.5 or 3.19, right? We can only see the integer values as responses to these variables. So, it's going to be a little bit different than for a variable where we could see non-integer values. If we want to be real theoretically correct, it doesn't just have to be integers. If you were looking at something like purchase orders or something, and whatever the product is, the company only sells them kind of in bulk, and so maybe you only can buy 10 at a time. Maybe think about something like I don't know, Ziploc bags, right? They sell them in larger quantities, and so maybe the responses I could see are only 0, 10, 20, 30, or something like that. That would be a discrete variable as well. But more often than not, it's when we can only see the integer values, okay? And it's a kind of finite number of values, right? So even though I can see 0, 1, 2, that doesn't continue off into infinity, right? You can kind of imagine the days you do something each week, that's a finite set. It stops at 7. Number of siblings someone has, I mean, I don't know what the highest number is, but it stops somewhere, right? I think whatever the largest family is, -1. So those are kind of how we think about, that's how we think about discrete variables. The next type of quantitative variable we have are continuous, right? So this is kind of like the opposite of discrete. There are no gaps in between the values we can see, so we can literally see any number, right? We could see 3.1597251, right? We could see whatever value you can think of. So from a number line, right, we could see 2, we could see 5, we can see 6.913, right? So we can see any value. So the easiest way to think about this is discrete variables typically are when we only have kind of these smaller integers, integer values that we could see for the variable. Continuous is where you could see really anything with a decimal on it. So anytime we're dealing with an example where you have like a decimal response, could be a response you see, we think of that as a continuous variable. So height and weight, you think about if we had a good enough measuring tool, we could measure that out to whatever decimal we wanted, right? We truly could see any value there. Okay? Salary, this one, you think about we have decimals associated with salary, and so that's a good example of a kind of a continuous variable. Now, I've had people, well, not many people in the past, but I always point out at this point, technically, by the definition of a discrete variable, if we think about salary, why could salary be considered discrete theoretically, if you want to really be a stickler on the theory? So we said that there's gaps in the values you can see for a discrete variable. For salary, what's the very first number you can see? The lowest salary you could earn is 0, right? What's the next highest salary you could earn? After 0, if I were going to pay you with money, what's the first thing I could pay you after 0?
0.1.
1 penny, right? What's the next thing I could pay you? 2 pennies, 3, so on. There's technically gaps in between that, right? Because I can't pay you with half a penny, right? Unless we're doing something like that. So, theoretically, you could argue maybe salary is kind of discrete, but we're going to treat, for the sake of this class, just for not to get kind of in the weeds about these things that are a little bit iffy. As long as we have a variable that has a decimal on it, we'll assume that it's continuous. And technically, income is. Like, if you look at actual pay stubs, you can get like 1/3 of a penny if it's just broken down. Like, so it's sometimes people kind of get stuck on that. But really, anything with a decimal we can think about as continuous. Also, this isn't a finite set, right? Salaries go from 0 to insanely high amounts, right? Whatever Jeff Bezos makes. So we got the difference there now. We can think about what we were doing earlier. This blank screen here for a reason. So we just broke down quantitative variables into 2 types, right? So we've got 2 different types of quantitative variables. One being discrete, we can think about these as integer values that are what we could see. And then we've got continuous, think about anything with a decimal. Right? That's how we're going to break down these two different types of variables. Qualitative and quantitative break down into nominal, ordinal, and discrete and continuous. Okay? And this becomes a little bit more important as we start working through some things later on in the course in terms of this discrete and continuous variable. We probably won't work with qualitative variables quite as much. Initially, we will get a glimpse into them, but they'll kind of pop up every once in a while. So, get rid of this, go through this, okay. Oop. And we kind of think about salary, right? If I truncated this just to kind of show it in PowerPoint, but these salaries did have kind of decimals associated with them. So salary here we have as a kind of a continuous variable from that Cubs data set. Okay? I just realized something. Let me see. Okay, now it's recording. I was going to say, I just had sometimes I'll do that, like 10, 15 minutes in, I panic and think I didn't hit the record button, like you left the oven on or something. So those are different types of data that we could see, but we have different types of data sets that we're going to be looking at as well. So really we have three types, right? I'm not going to kind of quiz you too much on this. I just want to make you aware of the types of data sets we'll see. So cross-sectional, excuse me, is when we have a bunch of different subjects at one point in time. So this would be like if I'm collecting, the GDP of countries all in 2011. Right? Time series is when you have one subject and collect data at multiple points in time. So this would be like if I just focused on the U.S. and looked at the U.S.'s unemployment rate for the last 10 years, right? Each year I look to record the unemployment rate for the U.S. So one subject, multiple points in time. Panel data is like mashing those two together, right? I'm taking cross-sectional and time series and combining them. So panel data is where I have multiple subjects. So maybe I have every single country. And for every country, I have recorded the unemployment rate for each of the last 10 years, right? So multiple subjects, multiple points in time. That would be kind of our panel data set. So we don't get into it too much in this course, but really panel data sets allow us to do the most, right? Or kind of come up with the highest amount of statistics and really are really the most desirable, okay? And it's because they have both components, right? They not only are able to look at multiple subjects, but they're also able to look at multiple points in time. Okay? So if we want to think about visually what some examples look like, I think this is the one I mentioned. For cross-sectional, so we have one point in time, 2011, and we have every country's GDP and education expenditures, right? So here, this is kind of multiple subjects, one point in time. That's our cross-sectional data, okay? Now, just because I have one point in time, I can still collect data on multiple variables, right? I can calculate not only the variable GDP in 2011, I can also figure out what the education expenditures were in 2011. So I can have multiple variables, it's just that they're all recorded at one specific time. Okay? Here was my kind of time series where I said we look at the US, we look at a 10-year time period and collect the unemployment rate. Okay? So this is kind of a nice time series. And I don't know if we'll get there today, but definitely on Monday, we'll talk about how we can put these time series data sets into a graph pretty easily as well. Panel data, so this is a data set I have laying around. It was I-STEP scores. And you've got student 1, student 2, student 3. So it's got a bunch of different students, and they're kind of all assigned a number instead of their name. And I've collected for multiple students their I-STEP scores at multiple points in time, right, or in multiple years. So, this is a nice example of a panel data set where we have multiple subjects, right, multiple students, but also collect the data at multiple points in time. Okay? Any questions? Shouldn't be anything too crazy yet. Okay with this? Okay. All right. Just do a brief kind of discussion of the difference between population and samples. This will start to be important next week when we talk about calculating measures of dispersion. So we've got population and sample data sets. So a population is if we had all the subjects that belong to whatever we're interested in drawing conclusions about. So this would be like, if I want to know the average income in the U.S., right? I'd have to have every single person in the U.S.'s income, right? That would be my population data set. You can imagine that's difficult to get for certain things, right? And we'll talk about that a little more in a second. But we sometimes try to collect this data, this population data, with a census, right? But we only do it every 10 years because it's very expensive and very difficult, to find the manpower to do. So more often than not, all we have is a sample, right? And the sample is just going to be some smaller set or a subset of the population. So this would be like if I was interested in the average income in the US, I can't get population data, but I can get like 2,000 random people and then start to use what I find from that sample to make inferences about the population. Right? So more often than not, we only have sample data. I kind of already talked about this, but the need for sampling, right? It's just difficult to get population data. Kind of thinking about if we wanted to do a census every single year, that's very expensive, right? If you think about kind of just sampling the entire population, sometimes it's not practical. It's expensive, but it's also not practical. Let's say I was interested in obesity rates in the US. So I go around and I start to record every single person's weight and height and muscle mass, whatever I need. Well, by the time I collect all that data, what's probably happened to some people's weight by the time I'm done? It's probably went up or down, right? So even if I was able to go around and record every single person's weight, I now don't have like truly factual information, right? So sometimes it's just not practical to be able to get population data, right? We have to kind of rely on a sample. So descriptive statistics, I'm not going to waste too much time on this. We'll kind of revisit this when we begin that because we'll mainly look at some tables and graphs today. But descriptive statistics are just going to be something that we're calculating that reflects some fact about the data. Okay? Statistical inference is the idea I already described, which is that if we only have a sample, I'm going to collect statistics from the sample and make inferences about the population, right? I'm going to assume that what I find from the sample is reflective of what the entire population is. So if I had population data, then this is what I'd be finding. So using the sample to make inferences about our population. And I don't know why I repeated that slide. I think I accidentally just moved things around, so we don't have to kind of focus on that again. So I don't know if we'll get to, I might show you a little bit in Excel today. But the first thing we're going to talk about, and we'll start with qualitative variables. Right? So the first thing we're going to talk about is frequency distributions. Okay? So frequency distributions start to give me an idea for one specific variable about where the majority of the responses are, right? So if I think here, I've got this looks like 10 people and a letter grade they got in the class, right? So all I'm gonna do with my frequency distribution is, okay, what are the possible responses I could see? Well, here I got rid of pluses and minuses, so I could see an A, I could see B, C, D, or F. Okay? So what I'll do is I'll go through and say, okay, the number of students that got A's is 2. So I'll go A and write the frequency down of 2, right? There was 2 students that had an A. Then for the next response, B, 1, 2, 3, I write that number down. There's 3 responses that are B, right? I do that for every single possible response, and now I have my frequency distribution. It kind of gives me these counts, right, of each possible response to where I can quickly look and say, okay, the most common grade in this class was a B, right? There was only a couple kind of lower grades, and then a little bit on either side of that most common response. Now, if we have a larger data set, this is a little bit more interesting, but it would the same not principle, the same process would apply. Okay, right? I would still go through and just count the number. If I had 2,000 students, I would count the number of A's, write it down, number of B's, write it down, so on and so forth. Okay. I don't think that's too bad. It's pretty easy. So we have this nice frequency distribution. I can then turn those frequencies into relative frequencies. Okay? So all a relative frequency does is say, well, look, you can see kind of the raw numbers here, but it might be helpful to have a breakdown like what proportion of the responses were B's for this variable, or what proportion of the students got D's. Right? So relative frequencies will tell me kind of that proportion. Okay? So all I do, right, let's just take a step back. Let's say I had 100 students, right, and 50 of them got A's. What proportion of those students would have had A's? So 50 out of 100 is 0.5, right? All you do is take that frequency of 50 and you divided it by the total number of observations, which is 100, right? Or the total number of students, okay? So once we have these frequencies for each category, for each possible response, A, B, C, D, and F, all we do to turn those into relative frequencies is divide by the total number of observations that we had. Okay? So once again, I had that Cub roster data sitting around, so I just pulled this because I thought it might give us a few more responses, which is I looked at all the players. There was 25 total players. I counted the frequency of each type of position on the baseball team. Okay? If I wanted to turn these into relative frequencies, all I would have to do is divide each one of these by my total number of observations, which was 25. Okay? So I can go ahead and do that, right, and get all my relative frequencies over here. This allows me to see, okay, for the majority of positions, they only make up about, what, a proportion of 0.04 and 0.08, but there's one position where I have a little over half of the observations coming from, which is this position of pitcher, right? So it allows me to identify that pretty quickly. You know, and that's maybe easy to do when I have a data set of 25. If I was looking at a data set of like 1,000, it's gonna be a lot harder for me to like pick out which position is happening the most often, okay? Now, one thing that I didn't want to gloss over, so here I added up the frequencies and I got this total of 25. And I was just kind of telling you and saying, this is the total number of observations. But if we think about why, if I have every response that I could possibly see for a variable, and I go through the entire data set and I count up the number of each one of those responses, every single observation will have been counted once, right? It have been counted in one of those categories. So once I have all those counts done, or I have all those frequencies, when I add them up, it should just be the total number of observations, because every observation should have been counted one time. So once I add all those frequencies up, I should get the total number of observations there. And then that's what I need to use to turn these into relative frequencies, okay? Any questions on that? Okay with that? All right. Oh, I kind of jumped the gun. You probably already saw it, but what should these relative frequencies add up to? 1. So why do these relative frequencies have to add up to 1? Well, if we think about what we're doing, first of all, if I've got my frequencies in the numerator, what should those frequencies add up to? We already said the total number of observations. So my numerators will all add up to the total number of observations of 25. And I divided every number by the total number of observations. So when I add all these up, I'll have the total number of observations divided by the total number of observations. That should just be 1, right? Anything divided by itself is 1, okay? So if you get to this point and you add up your relative frequencies and they don't add up to 1, you know you made a mistake somewhere, right? You can go back and try to figure it out, but you made a mistake if your relative frequencies don't add up to 1. Excuse me. So the next step, and this is sometimes where people get a little bit confused early on with terminology. So a lot of the times when we're looking for things like a relative frequency, I said another way to think about that is it's a proportion, okay? A proportion can only kind of be between 0 and 1, right? Once we get up to the total number of observations divided by the total number of observations, that's the highest we could ever see, that's 1. The lowest we could ever see is nothing happens, or we never see a particular response. So 0 divided by the total number of observations will always be 0. So our proportions are between 0 and 1. Now we can turn those, or we can say those as percentages, right? If I have a proportion of 0.5, so I say the proportion of the students who got A's was 0.5, then the percent of students who would get A's there would be what? Proportion of 0.5, 50 out of 100. What percent of students would we say that is? 50 out of 100 is 50%, right? So what did you do there to move between the proportion and the percentage? Well, the proportion was 0.5, the percentage was 50, you multiply by 100, or you move that decimal point 2 places. So the only difference between proportions and percentages is really we're just moving the decimal point 2 places and saying percent on the end. I mean, that's a lot more how we speak. Like, you know, if you were going to describe something to someone, I don't think you'd say, you know, Well, the proportion of 0.5 of the time it happens. No, you say 50% of the time it happens, right? We speak in percentages, but a lot of times what we need when we're doing some of this computation is we need to think about these as in their proportion form or kind of decimal form. Okay. So, you know, how would we then get a percent frequency? Well, we've got the relative frequencies. Those are proportions. We simply take that relative frequency for the category, multiply by 100. Right? It's as easy as that. Okay. Once we do that, we could, once we do that, we would then have the percent frequency of the category. The percent frequencies, if the relative frequency should add up to 1, the percent frequency should add up to what? 100. Yep. So we could think about if we had like a sample data set like this, and this might be something in the future, like we work through an example like this, and then I show you an example very similar for the online quiz, right, that I asked you the question. So here we've got what? Leading causes of death for looks like a 7 to 8 year time period. Here we've got our frequencies. So it's like someone already went through the data set and did the frequency distribution for us. They went through all these death records and found that 5.3 million came from heart disease, about 4.4 came from essentially cancer, 1.2, I'm not a science, kind of hard science guy. So, you know, we could go through these different types of diseases and we've got the frequency or the count for each one. If we add all these up, if we add our frequencies up, we should just get every death should have been counted one time since we have this other causes category. So if we add up all those frequencies, they should add up to the total number of observations or the total number of deaths that we saw in the US over this time period. So over this time period, we have about 16.6 million deaths, okay? So how would I turn these into percent frequencies? Well, the very first thing I would need to do is what? I'm looking at malignant neoplasms, and I have the frequency. To turn it into a relative frequency, what would I divide by?
The total.
Okay. My total number of observations are about 16 million. Okay. Then to turn it into percent frequency, I would then have to multiply by 100. Okay. So, you know, I'm going to rough estimate this, even if without a calculator. It's about 4 million out of 16 million. So that's about a fourth, or a proportion of 0.25. So 0.25 divided by 100, about 25%. Now, if I gave you the possible answers as these, well, I rounded pretty grossly there to get my 4 and 16 million, right? So it's probably going to be a little different than 25%. If we actually end up calculating it, you know, 4.4 million over 16.6 times 100, we get about 26.8%, right? Well, this is one of those things where even if we have a formula as we go through the class, I'll continually try to make this point. Don't get too lost in the computation or in the formula. Still remember what you're trying to do or what the statistic you're calculating is trying to tell you. Here, we're looking for basically what percent of the overall deaths came from these malignant neoplasms. Well, if I just look at this and I say, well, this is one of the higher number categories, 4 out of 16 million, that's a pretty good percent. Even if I can't do that exact math in my head, 4.4 divided by 16.6, I know that percentage should be a lot higher than 0.27%, right? You know, but I have to kind of make sure I'm looking and seeing that there are percentages here, because if I forgot to multiply by 100, I would have had about, what, 0.268 is my proportion. So trying to rule out answers that just don't make any sense, kind of stepping away from the equation, would probably allow us to rule out B and C, right? It just looks like it's way too low of a percent when I'm looking at 4 out of 16 million. Okay? And you could calculate that for, you know, so sure enough, we plug in the exact numbers, we get about 26.8%. You could do that for any of the other categories as well, come up with those percent frequencies, and you do it the exact same way. And we kind of already mentioned what should those add up to? Should add up to 100%. So if they don't, we made a mistake somewhere. Any questions on that before we keep moving? All right. I think what I want to do. We got one. Okay. I think I'm going to do a little bit of Excel today, just so we can get our first kind of taste of it. So I'm going to start out basically assuming you know nothing about Excel. Right? So we'll just talk through some basics, just some things, maybe terminology even that I'll use. And then I might make a quick little data set here and kind of show you how to use a function that's built into Excel. So let's say, I don't know, I've got this base of 100, okay? And I want to add, I don't know, 50. Let's say, you know, I want to add 50 to whatever the base is. The base just happens to be 100. Doesn't matter necessarily the example that we have. So I go equals sign. So when we're in Excel, right? If I put an equal sign, that tells Excel I want you to do some math for me, right? Or I want you to perform this built-in function that does some math for me. Okay? Now here, all I want it to do is set this equal to whatever value is in the cell that I referenced. So cell references are really the power of Excel, right? And every cell, so I'll get out of here for a second, right? This is cell A1. This would be cell D3. This would be cell F3, right? Kind of the row and the column labels give us the cell reference, right? So anytime I use a cell reference after this equals sign, it's basically going to go to that cell A1 and use the value that's in A1. So if I hit enter here, it should just show me 100. Now, if I go back and I change the cell that I referenced to 50, notice that cell reference will update. Right? So if I'm using like some original value and I'm doing a bunch of work with it, the nice thing is if I keep using that cell reference and that original value ever changes, all I have to do is go back and change that initial cell and everything else will update. Right? So we'll start out with 100. Right? And kind of see, even if I wanted to do some additional math, so maybe I wanted to add 50 to that original value. Hit enter. Well, I added 50. If I go back and change the original cell, once I hit enter, this should update and still only add 50 now to my new value. Okay? So that's how we can use cell references. Now, let me do something a little bit different. So I'm going to put 50 here, 100 here, 150 here. Okay? So instead of adding the 50, I'm going to use a cell reference that has the value of 50 in it. So instead of typing in D1 to add the 50, if I just click on it, it automatically puts that cell reference in there for me. Okay? So now I'm going to hit enter. Right? So when I copy things down, okay, if I were to copy this cell down one, every cell reference I have will update whatever direction I move it. So if I move it down one row, both of my rows will also get updated by one. So instead of 1, when I copy this down, instead of A1 and D1, it's going to use A2 and D2. Okay? Now that's good if I want to say, instead of adding 50, add 100 to that original value, right? But the issue is going to become, if I try to copy this down, okay, it is using the next value, right, that was in the column over, but my original value of 100, that cell reference was also updating, and I wanted to keep that the same, right? Maybe, you know, in this cell, ultimately what I want is 100 plus 50. In this cell, what I want is 100 plus 100. In this cell, what I want is 100 plus 150. Okay? Well, if I go back, so I delete this, I did want this to kind of keep updating, all right? I wanted that cell reference D1. When I copy this down a cell, I want it to be using the value in D2. When I copy it down one more, I want it to use the value in D3. But when I copy this down, I always want to keep using that value that's in A1, that 100. So how we can stop that cell reference from updating is if we put dollar signs in front of the row and column heading. Now when I copy this down, this tells Excel, don't change A1, like don't update it one row if I copy it down one row. Okay? So I'll hit enter, drag this down. Now, sure enough, it's kept A1 the same, and now it's just adding in that value in D3. Okay? So these cell references, we can freeze them. We can also allow them to update. Allowing them to update allows us to do multiple calculations at once without retyping the formula. I just have to kind of copy it down. So we'll kind of see the power in this and some other uses here as we work through Excel. But this is just some kind of basics. Okay? Any questions on any of this yet? Okay with this? You guys are being kind of quiet. So. All right, so the other thing, just in some terminology, a lot of the times we'll have different worksheets in the same workbook, right? So we can do things, we can, rename them, I don't know, numbers. So we can name, these sheets whatever we want. Now, a lot of times when I post these on Canvas, let's see, this might actually be one of these files. So, oh, I didn't post anything up there. Sorry, let's do the seating chart. If I just look at this on Canvas, first of all, this looks like a mess, right? But a lot of the times, if you look at it on Canvas, you may only see kind of the first sheet. So we'll look at the seating chart. So notice, even if we open the seating chart, I've got different worksheets down here. So anytime you open the file, if you're like, this doesn't look anything like what he's referencing in the homework, well, there might be multiple worksheets, right? So make sure you're on the right worksheet. So here we've got multiple sheets. So I'm gonna do something here on sheet 2. And all I did to add that in, right, was click on this little add button here and it starts putting in new sheets. Okay? So let's say, I don't know, I've got a bunch of cars. Oops. Oops. All right. And I've got a bunch of different colors that they could be. Okay? So I'm going to write down all the different possible colors that I just wrote in. I think that's all. Okay? And you can kind of imagine, I might have a much longer set of cars here. So instead of counting these by hand, let's do the frequency distribution using something that's built into Excel. Okay? So like we saw earlier, I can have Excel do math for me, right? I can put an equal sign and say, take 100, divide it by 50, put parentheses around that, and then, I don't know, subtract 20. Right? I can do something like that, and it does math for me. Right? But I can also just put an equal sign and then say, okay, Excel, you have a built-in function, right? So usually when we're talking about things like this, I'll call this a formula or an equation when we were just using Excel to do math. But an actual Excel function is something that's built into it. So something that's built into it is something called a Countif function. Okay? So if I put equal sign Countif and then a parenthesis, it kind of tells me, look, this function has two things you need to tell it, the range and the criteria. So the range, what this Countif function will do is look through a bunch of observations and count that observation that meets a certain criteria. So if I want to count the number of observations that have red as a response for car color, I can look through the range of data and count the observations where the car was equal to red. So how we'll do that is, the first thing we'll do is select the range. So all that means is select all of your observations, right? And I just selected with my mouse, held that left mouse button and dragged down over the data. Right? Now another nice little shortcut, and this is more useful when we have really large data sets. So let's say I had like 3,000 cars here. It's going to take me a while to drag all the way down with my mouse. So what you can do is click on that very first observation, hold Control Shift, or on a Mac, Command Shift, hit the down arrow, and it will go to the very last observation in that data set. So Control Shift, or if you're on a Mac, Command Shift, hit the down arrow after you've selected the very first cell, and now it'll select the entire range for you. Okay? The next thing we need to tell it is what criteria are we trying to check to make sure if it's true, right? We only want to count it if it's equal to the word red. So comma, so we select the range, comma, then tell it the criteria. So what we want to know is it equal to, right? Is the observation equal to the word red, right? Does it have the word red in there? Well, just the kind of syntax of Excel, we need to put quotation marks around the equal sign, okay? Then we'll use this and sign, right? And this has something to do with the way that this function recognizes what you're about to tell it next. So we want to check is it equal to the word red? Well, I already have the word red written in here. So instead of typing in the word red, which I could do, so I could put in that word red. Right? Now I had to put that in quotation marks because that identifies to Excel that this is text, okay? So if I hit enter here, what answer should I get? What, 1, 2, 3? Sure enough, it counts up that there's 3 red cars. Okay? Now instead of using that word red, what I would suggest doing is just having red in another cell and clicking on that cell reference. So now it's going to count it if it's equal to the word that's in cell C2. The word was red, so it still should get 3. So there's a reason why I kind of put these colors in a row here, because instead of typing this out, 6 different times, and each time, one time typing in the word red, one time typing in the word blue, now if I copy this down, if I copy this down one, it'll be looking at cell C3. So the next cell would give me the count of cars that aren't red, but that are blue. And when I copy it down another one, it would go from C2 to C4, and it would count the number of cars that are yellow, and so on and so forth. Okay? Now, what's going to be one issue if I do that, right? If I copy this down, okay, it looks like everything worked okay. But notice when I reference the data, that cell reference updated as well. Now I'm actually not looking at, I'm skipping the first observation, okay? So how can I fix that in the kind of original COUNTIF function I had? Yeah, put the dollar signs, right? Freeze it so this doesn't change. I always want to keep using the same observations. So a nice little shortcut we can use here is, so there's 3. If you're on a Mac, if you hold Command T, right? Or if you have a computer, F4, or some laptops have an FN key, mine does, hold FN and then hit F4. Whatever you've selected, it will automatically put dollar signs in there for you, right? So Command T on a Mac after you've selected this, F4, or if you have an FN key, FN F4. Okay? Now when I copy this down, I'm still using the original data, and I'm allowing that car color reference to update, okay? I'll kind of leave that up there. So we're kind of running low on time here. So I think this is kind of a quick glimpse into how we would do frequency distributions with qualitative variables. You can imagine if I had a much larger data set here, this would be really helpful, right? And we'll start to look at some larger data sets to see, next class I'll bring up an example where I show you even with like 12,000 observations, using that shortcut to select the entire data, it's pretty easy, okay? Like I said, the online quiz today will be due before class on Monday. Because it has questions related to kind of the showing up for in-person classes, and I kind of want to try to get a list together before class Monday. If you can please try to get on and get that done today, that would be really helpful so I can start to look to see, get a more accurate number about how many people we're going to have who want to attend in-person classes. But it is technically not due until class starts on Monday, okay? We'll work through some more Excel examples on Monday. What we have worked through, once we finish it on Monday, I'll save this file and then kind of post it up on Canvas so you can kind of see what we worked through. Get that second Learn Smart assignment done, just real easy, 10, 15 minutes. It's more so to just make sure you're getting an access code. And if you have any other questions, feel free to reach out. Other than that, have a safe weekend. I'll see all of you guys next week on Friday, very least, and hopefully some of you on Zoom will be attending on Monday. Okay.